Hello and welcome. Thank you for joining us today for the AWWA webinar sponsored by Evoqua on chlorine dioxide measurements and protocols to successfully manage residuals. I'm Glenn Holden, Corporate Accounts Manager for Evoqua Water Technologies based in Houston, Texas. I'll be your moderator for today's webinar. And I'd just like to go through some tips first to enhance the webinar for you. First, there are a few tips. We would recommend you close email, instant messaging, and any other programs not currently in use, as they could interfere with the smooth reception of the webinar, causing slide buffering and poor quality sound. Technical assistance, if you need it, can be found at the GoToWebinar technical support page at the link that's listed in your handouts and on the slide that's shown above. And one point I'd like to make is there will be a survey at the end of the webinar. The survey window will open. This is after the question and answer period. And as soon as you close the GoToWebinar screen to leave the webinar, there's going to be a window that will open with the survey questionnaire. We'd sure appreciate if you could respond to that survey. Your feedback is really important, and it helps us and AWWA to improve the webinar programming. We would really encourage group participants that are online to pick one person to enter collective responses to the survey and then submit them to us. Secondly, before we hear from our speakers, I need to really inform you that the mention of any specific products or services in the webinar really does not represent AWWA endorsement. AWWA doesn't endorse or approve products or services. I think this presentation is fairly generic, so I don't think we'll have a problem there, but I want you to be aware of that. The next slide I want to give you is the agenda for today's presentations. First, there'll be an introduction to the presenters. There'll be a short technical overview that I will go over in terms of what is chlorine dioxide, how it's produced, why it's important, some of the implementation factors. Next slide, please. The residual analysis, which is a lot of what we're going to be talking about today, along with online monitoring tools. We'll summarize at the end of the presentations and then open a session for questions and answers. The presentations are going to be about a little over an hour long, and then we have about 20 minutes for questions and answers. Today's key presenters are Dr. Bernie Bubness. Bernie will be talking about measurement protocols to successfully manage residuals. Bernie is the president of NovaChem Laboratories in Oxford, Ohio. He's just a really reliable partner with a lot of experience working with numerous utilities, water utilities, and manufacturers of chemical oxidants. A lot of experience, especially in the measurement of low-level disinfection byproduct concentrations, things like chlorine dioxide, chlorite, chlorate, bromide, and bromate in drinking water. Bernie will give a little more intro in terms of what his laboratory does in a moment. The second speaker will be Stefan Andre. Stefan is a global product manager for Evoqua Water Technologies, lots of years of experience in online measurements of chlorine dioxide, chlorite, chlorate, etc., residuals, online monitoring tools for residual monitoring. Next slide, please. There's a picture of Bernie and a picture of Stefan. If you have questions that you want to pose during the webinar, there is a lower right screen that you'll see that you can include your name and specify to whom you're addressing the question. I'll repeat your question at the end of the these sessions, and address it to the right individual on the panel. Next slide, please. So, first off, I want to give you a brief introduction on chlorine dioxide. What is it, how it's produced, etc. At room temperature, chlorine dioxide is a light-sensitive gas. It's denser than air, has a slight yellow-green color to it, very soluble in water, and it has a chlorine-like odor. And you'll see the molecular structure there on this slide, just to the right. Next slide, please. In terms of chlorine dioxide belongs to a family of chemicals that are known as oxidizers, but it's also a very powerful disinfectant. Some of the other oxidants are ozone, hydrogen peroxide, obviously chlorine, and of course chlorine dioxide. They're all measured basically on oxidation reduction potential. But the key point I want to make on this slide is that, please go back to that slide we just left. One of the key points I want to make here is that if you look at the ORP, that is a measure of the strength of the oxidant. Ozone is at the top. If I had the hydroxyl radical, it would be slightly above ozone. Chlorine dioxide, dissolved in water, has an ORP of about 0.95. The unique thing about chlorine dioxide is it can transfer up to 5 electrons in terms of oxidation reduction reactions. So it has a very high capacity. The other unique thing about it that I mentioned to you is that it's also a very powerful disinfectant. Because it's a relatively weak oxidant, one can get a residual, just like you would with chlorine. May not be as long life as chlorine, but you can get a residual with chlorine dioxide. Next slide, please. So, how is chlorine dioxide produced and delivered? It's best supplied via on-site generation systems. This is special equipment. It's just simply too energetic to compress, package, and ship down the highway. It's shock sensitive, it's pressure sensitive, it's heat and light sensitive. So typically it's produced on-site using special equipment. And that requires starting chemical raw materials. So all chlorine dioxide is produced from one of two starting precursors, sodium chlorite or sodium chlorate. The sodium chlorate is reduced via reaction with an acid such as sulfuric acid and a reducing agent like peroxide to produce chlorine dioxide through, again, a chlorine dioxide generation system. The sodium chlorite ion is oxidized via a reaction with chlorine, and there are non-chlorine gas methods of producing chlorine dioxide from chlorite that are quite popular today, and that usually involves the production of chlorine in situ under vacuum from a reaction of bleach plus acid. Next slide, please. This is an example of some of the equipment that I mentioned. It's just a generic 2 redundant chlorine dioxide generation systems installed at a water plant, potable water plant. These are actually batch generation systems. They produce a chlorine dioxide solution of about 2 grams per liter, 2,000 parts per million, dissolved in water to a FRP batch tank that sits on the back side of those skids. And in this particular case, there are 3 output dosing ports. So each of those systems could deliver chlorine dioxide to up to 3 injection points. Typically, it's either 1 injection point, sometimes it's 2, sometimes it's 3 or 4. But there are systems that are available in the marketplace that can deliver to multiple injection points. Next slide, please. So why chlorine dioxide? I would assume many of you on the webinar today are already familiar with chlorine dioxide, but then maybe not. First, it's a very cost-effective disinfectant. It's used to meet compliance goals for phase 1 and phase 2 disinfection byproduct rules, and also as an aid to meeting compliance rules on the long term to enhanced surface water rules. It's a very broad spectrum disinfectant. It's effective from pH 2 to 10. It's not impacted by pH like chlorine, for example. It can provide CT disinfection credits for crypto, giardia, viruses, bacteria. It's known to assist in the control of algae and also mollusks like zebra mussels and Asiatic clams, for example, quasi mussels, another one. It's EPA approved, federal EPA approved for primary and secondary disinfection. Next slide. Secondly, it's a very selective pre-oxidant. You may recall in one of the earlier slides, I showed you that on an ORP scale, I had an ORP of 0.95. That's the aqueous dosing solution of chlorine dioxide. It is, because of its relatively low ORP, it's very selective in terms of what it will react with in comparison to something like peroxide or ozone. It rapidly oxidizes manganese to manganese dioxide, iron to polyferric hydroxides, and these are insoluble forms. It's typically applied to raw incoming water as a pre-oxidant to oxidize the manganese and iron, which then gets removed typically via coagulation, flocculation, or microfilters, membrane systems, for example. It will oxidize certain organic carbon, DOCs and TOCs in water. Sometimes we call it naturally organic matter, NOM. And by doing that, it puts these oxidized organics in a form that don't easily get chlorinated by chlorine. Thus, it reduces trihalomethanes and total haloacetic acid formation. What we typically see in most surface water plants where chlorine dioxide is dosed to the front end raw incoming water ahead of coagulation and flocculation, and followed by either chlorine or chloramines to distribution, we would typically see a 30 to 50% reduction in trihalomethanes, trihaloacetic acids, and that would be typically by replacing chlorine on the front end of the plant with chlorine dioxide. Because it does oxidize manganese and iron very rapidly, the kinetics are very favorable for chlorine dioxide in that reaction. It typically will enhance filter runs pretty dramatically, improves clarity, turbidities, taste and odor aesthetics of the water. And one of the unique things about chlorine dioxide, its disinfection byproduct, the chloride ion, has been shown in multiple studies now to help control biofilm and nitrification issues in piping systems. This is especially important where chloramines are being used and there are nitrification issues out in distribution. It doesn't take much chloride ion or chlorine dioxide ion to do that, typically about 0.3 to 0.4 part per million, which is significantly less than the MCL limit on both chlorine dioxide and chlorite. Next slide, please. Lastly, why chlorine dioxide? Well, it provides superior DBP control. The residuals of chlorine dioxide are measurable. They're well studied. We're going to be talking more about that in this webinar. Chlorine dioxide won't itself oxidize bromide to bromate. Doesn't react with ammonia. It doesn't itself create THMs, THAAs, or NDMA, nitrosodimethylamine. It's quite compatible in multiple barrier treatment processes. It's applied ahead of membranes and microfilters. It's used with chlorine and chloramines, often dosed ahead of chlorine or chloramines, but it can also be co-dosed. It can be applied pre or post ozone. Why would you do that? Typically to reduce the demand on ozone, and particularly in waters containing high bromide levels, that will help control the bromate ion and meet MCL limits. There are a number of utilities doing that now around the country. It can also be used pre or post UV. Next slide, please. So what typically is involved in looking at chlorine dioxide for, say, a new user, typically the chlorine dioxide systems manufacturer would do a system survey on site, might do some reactive demand tests and piloting. Often that is conducted by the consulting engineering firm associated with the project. There's specification and technology selection of the equipment that's going to be used, raw material selection. Most commonly across the U.S., the equipment, the chlorine dioxide generators, are NSF 61 certified. That's by state requirements. Not every state requires that, but the majority of them do. The raw materials in almost all cases for potable water treatment are requiring NSF 60 certification. That would be particularly on things like sodium chlorite or sodium chlorate, bleach, etc. The acid that might be used in the process as well. There's typically permitting and compliance rules that have to be met, and a big part of that is the monitoring plan for chlorine dioxide and the chloride ion residuals to achieve MCL limits and MRDL limits at entrance to distribution and also out in distribution. Bernie is going to be talking a lot more about that, as will Stefan in their presentations shortly. And then lastly, once all of those things are done, a permit has been issued by the state EPA. There's installation, training, commissioning services, a program that needs to be looked at strongly with the chlorine dioxide manufacturer or the contractor or both. And then last but not least, very importantly, are the preventative maintenance and seasonal optimization programs that are really needed. Training is part of all of that to maintain the chlorine dioxide system at its optimum conversion efficiency and purity of chlorine dioxide that's being dosed. Next slide, please. So I'm going to turn the presentation over now to Dr. Bubnas of NovaChem. Bernie is going to be talking about chlorine dioxide measurement to successfully manage residuals.
Thank you, Glenn. Welcome to everyone to this webinar presented by Evoqua. I want to thank Evoqua for inviting me to speak a little bit about making measurements and how to successfully manage residuals once you apply chlorine dioxide. Next slide, please. NovaChem, you may recognize the name Novatech. That's what we were originally organized as, have since gone through a name change. And we were involved in the early discussions with the EPA on how to accurately measure the inorganic ions. Over time, many changes have occurred in the industry, especially the laboratory business. And now to provide data to the regulating agencies, laboratories should be NELAC or state certified. And what this process is there is a standard out where each laboratory has to meet the standard to provide good quality control. So a quality assurance plan is prepared and maintained. Part of that is one has to measure proficiency tests at least twice a year, and of course, pass the test. NovaChem, we assess residuals using a variety of different test methods. I believe personally that you need to have, in times where there's lots of questions, you really should measure by two different methods to verify. So in the toolbox that we're using, there could be a variety of titration methods, some ion chromatography, perhaps using some things like pretreatment cartridges to remove certain substances. And at times, spectrophotometry does come in real handy, for instance, in demand testing at higher levels. Next slide, please. But typically, the measurements are needed really to focus on three things. They really help you determine treatment strategies. They help you maintain the efficient operation of your hardware. And then at the end of the day, you do need to show that you are indeed in compliance with the regulations. Next slide, please. So when you're determining a treatment strategy, you really want to know how much oxidant is there to use? What is the appropriate dose? You also want to set up and design, test to see where is it best to introduce the oxidant. Is it better apply it up front or somewhere else in the treatment train? So you can design studies to do these things. And once you design the studies, you certainly make the measurements to evaluate the placement of the where you're going to dose, and also to verify that you're meeting your goal of its use. So you need to evaluate all the preliminary studies, and your engineering firms are quite adept at that kind of thing and will help you make the best choice for your utility. Next slide, please. When you look at oxidant demand, there's a number of different things with chlorine dioxide. In this first demand curve, what we're doing is we're varying concentration and measuring at the same time point. So time is constant. And as you see, if chlorine dioxide is on the bottom and the upside is the measured residual, you'll see that typically, let's say at a 1 part per million added dose, you might see around 0.8. That's really quite typical of what you can expect. It really depends on water quality. I have measured some samples where I've got complete, well, if there's no demand, you're going to get 1. But if you're going to measure the chlorine dioxide, all the residuals, you'll see somewhere around 0.8, 0.7 for total residuals. Next slide, please. And why is that? Well, a typical demand curve really looks something like this. You're measuring some dose of chlorine dioxide at some defined pH and some defined temperature. A lot of people like to measure it at 2 temperatures. They'll measure a summer temperature and they'll measure a winter temperature. Why would you do that? Well, in the summer, of course, it's warmer, and as the temperature goes up, the reactions speed up. So you want to know how fast you want to see how fast you're reacting chlorine dioxide, or how the demand, what they call the demand, how it changes over time or over against temperature. Again, the mass balance, you're looking at chlorine dioxide, let's say at 3 milligrams per liter. You have this very rapid decrease because chlorine dioxide will react quite quickly. And at the same time, you'll have this rapid rise in chlorite ion. And as you can see at about 1.5 ppm, you can see they're about equal. And then it'll tail off and still react, but at a much slower rate. And again, the whole time chlorine dioxide will decrease. You'll see a slight chlorate. Typically, you'll see a slight chlorate ion residual. How long will chlorine dioxide remain? Well, it really depends on the quality of your water and the dose. And so if you have very clean water and you're using a medium range dose, let's say maybe 0.75 part per million, you may, but it has to be really clean water, you may see a chlorine dioxide residual after 90 minutes. I've measured things like harbor water where it's pretty filthy, the water, and the chlorine dioxide within 3 minutes, a dose of 2 milligrams per liter or higher is almost goes to 0 in less than 5 minutes. So why do we have maybe only 80% recovery? Well, some of the chlorine dioxide might continue to react, and you might see some chloride ion increases, and there are some reactions with humic matter that will react both with chlorine dioxide and with chloride ion. Next slide, please. So if you look at this, the measurements are really providing information. And again, what we're trying to do here is to find out how much chlorine dioxide is going to be required to meet our goal, and where's the best place to position the dose. And so you can do those with some demand testings if you design the experiments properly. Again, Temperature is important, so you may see a little dose requirement change when you're comparing winter versus summer. However, pH, chlorine dioxide, really, you probably won't see many changes with pH, certainly over the 5 to 8 pH range. And again, what you really want to do here is measure the residuals. You want to measure how much chlorite is there, how much chlorate might be there, although for chlorine dioxide right now, chlorate's not an issue, but I will touch on some interesting characteristics a little bit later in this presentation. Next slide, please. It's very important to maintain your equipment. And so you need to make measurements. As you can see from this equation, something called yield. We're looking, if you think of the demand curve and you think of the components of the demand curve, we're trying to maximize the amount of chlorine dioxide as a percentage of the total residuals that might be present: chlorine dioxide, chlorite ion, and chlorate ion. So it's important to have efficient equipment because feedstock costs. And so you want to convert your feedstock efficiently to you want to get the most chlorine dioxide you can get out of it. So you need to make that measurement. Next slide, please. In the industry, something called purity has been brought up time and time again. And purity, you really, you want to be putting chlorine dioxide in as pure a form as possible. So in say a chlorite ion generator, you would look at, and there are many different types, but what you try to do is on the denominator, you put the possible precursors that maybe could break through or could be formed, and then you divide the chlorine dioxide by that. The industry standard is 95%. So, for instance, if you were using a chlorate generator, you probably would want to know if there's any excess acid because you're using a little acid to drive the reaction, or if there's any excess peroxide. So you would change the denominator to accommodate that. Next slide, please. Also important is chlorine. Now, chlorine, of course, the more chlorine that's in the system, probably the higher your THM values are going to be. The industry suggestion, of course, by the EPA is to have a maximum of 5% excess. So you have to make the measurements, and then there are equations and documents that will show you how to calculate. Here is one of the equations. Next slide, please. So if we're going to summarize about keeping equipment efficient, you really need to optimize the feedstock conversion. You need to identify any chemical precursor imbalances and make adjustments. I get calls and people say, well, is my chlorine feed too low? Is my chlorite feed too high? This is why you make these measurements to determine what is the best way to optimize your generator. And importantly, again, because we're talking about controlling and managing byproducts, we really do want to maintain operating levels less than 5% excess chlorine. Again, chlorine can oxidize and it can chlorinate. Chlorine dioxide only oxidizes. So if you can lower the amount of chlorine, I think it's demonstrated that you'll have better and lower residuals. Next slide, please. The regulatory requirements for the maximum contaminant level, which is called the MCL, and the maximum residual disinfectant level, the MRDL, are shown in this slide. And for chlorine dioxide use, we're really looking at an MCL of 1.1 milligram per liter and 0.8 milligram per liter for chlorine dioxide, 1 for chlorite ion. Next slide, please. So part of the regulatory requirements is to take samples and make measurements. And so when you're measuring chlorine dioxide, you need to sample daily and make a measurement daily. For chloride ion, they're asking also for a daily measurement at the entrance of the distribution system, and then 3 samples going out monthly to some other lab that typically is for an ion chromatography measurement. The first sample will be someplace close to the first customer. In Texas, for instance, TCEQ wants you not to supply the plant value. They want the first sample to be outside the plant, preferably right around the first customer. And then the other ones are self-explanatory, somewhere where the average residence time and then the location of the maximum residence time. Next slide, please. We're talking about chlorate, and inevitably perchlorate ion as residuals. These questions come up. At the present time, there's no testing required. It's my opinion, and I have a pretty strong opinion of this, that the perchlorate ion and a lot of the chlorate ion is largely due to the decomposed bleach that's applied to a system as a system residual. Here's why. Next slide, please. Bleach decomposes. It's going to happen. It decomposes faster in warmer weather, slower in colder weather. There's a temperature dependence. But when bleach decomposes, what happens is it's at an alkaline condition, so it's in the form of hypochlorite ion, OCl-. 2 hypochlorite ions will form chlorite ion, which is a steady state intermediate. It doesn't build up based on bleach decomposition. The chlorite ion will react with another hypochlorite ion to form chlorate ion. Now, the stoichiometry obviously is 3 hypochlorite ions. You can count them. The first reaction is 2, the second reaction is the third, and it will form chlorate. There's also something that you need to be aware of if you're using bleach as a system residual. Bleach can form oxygen. And there's a low-level uncatalyzed reaction that'll form oxygen, but there's also a catalyzed reaction, which means that if you have metals in your bleach, you'll get some bloating and some off-gassing. And a lot of places you'll see this. I've even seen it in supermarkets in the liquid bleach that are on the shelves. You'll see a bottle sometimes that's deformed and kind of tilted and it's bloated, and that's because the bleach has some metals in it, and so that's the catalyzed reaction. Next slide, please. I should say the catalyzed reaction again is caused by transition metal ions, and the industry has the bleach manufacturing industry has found ways to overcome these, so it's really possible to get good bleach. So in chlorine, liquid bleach decomposes. I'm talking about when you're storing bleach before you put it in. You don't want to, I think now most people are going to stored bleach as opposed to chlorine tanks. So when you're storing it, from the time you put it on your site, it starts decomposing, guaranteed. And if you look at traditional bleach, which is the second line, you'll see that it decomposes much faster than this is a low salt bleach. And so when you're thinking about buying bleach or something to use as a system residual, you might want to keep in mind other available things. There are differing products out there. But the important part is that if you don't get a higher quality bleach, you're going to get a lot more decomposition, and that means a lot more chlorate ion. Next slide, please. I should say bleach decomposition is dependent on pH, temperature, concentration, time, and ionic strength. So there's factors that you can control. So we're talking about chlorine dioxide primarily here today, but what's the effect of this decomposing bleach if you're using it on site? And I know right now it's not regulated, but I do have people asking me the question, how does it, what kind of level can we expect? Well, if you look at the level from 0.05 to about a half a part per million, you're talking about 55% of the cases in this survey. It was done under an AWWA Research Foundation grant through Miami University. And we did this testing, and that's a pretty substantial chlorate value. And then there are some places that clearly the bleach was sitting around for a very long time. Something for everybody to be aware of. It's just something you need to understand happens, but you can make adjustments on site and control it. Next slide, please. If you have a chlorate problem, you may be setting yourself up for a perchlorate problem. Again, perchlorate will form in the bleach, and it's strongly dependent on temperature and ionic strength. Again, another Research Foundation project identified a number of factors that are important in its decomposition and its formation. The rate law, the rate constant are presented here in this slide. Next slide, please. So again, as bleach decomposes, you will get a buildup of perchlorate, and this is over 30 days. I just want you to get a feel for what you might be seeing. You're talking 10 milligrams per liter, starting with a 12% over 1 month storage period. So, and it will continue. Once you make perchlorate, it's not going anywhere else. Next slide, please. So, if you manage your chlorate, you'll manage your perchlorate. Again, they're not regulated right now. Bleach decomposition is the likely source, but we can take steps such as some people refrigerate, some people dilute, some people use lower ionic strength bleach. There are ways to get around it. So you can take care of it. You just have to understand that it's there, and you have to know how to make the adjustments. Next slide, please. When we look at testing, first thing we look at is we need to make sampling. So if you're going to do, well, the very first thing is that it's tough to send chlorine dioxide samples off-site. Actually, you really shouldn't do that, and if you do that, you should stop doing that. You should make this measurement within an hour or two maximum. You have to fill an amber bottle to overflowing from the bottom, leaving no headspace, and measure it as soon as possible. Why is that? Because chlorine dioxide reacts, and you need to chill it down and get the test done. If you're measuring chlorite, well, that's a little bit different. If you're going to do ion chromatography, what you really need to do is you degas it to get rid of the chlorine dioxide. Why do you do that? Well, when chlorine dioxide reacts, it forms chlorite. So if you don't remove it by displacement or remove it, what happens is you're going to have elevated chlorite levels. Secondly, sometimes there might be a system residual of chlorine or something, so you need to mask the chlorine. I will say there are no masks for chlorine dioxide, but for chlorite we can add ethylene diamine, which is EDA, and you put about 50 ppm per 100 milliliters. In the EPA method 300.1, there's a formula that tells you how to prepare these kinds of solutions. The holding time is 14 days. If you're measuring generator samples, you really still need to, well, you obviously need to degas the samples, but you may need to degas vigorously for up to 30 minutes. And then you can take the samples and measure for chlorite and chlorate ion. Next slide, please. The methods that are approved and we suggest that you consider are method 4500-ClO2E, the amperometric titration, which is really a sequential method, and it's you measure differences of differences, so there's some error in the measurements, but it's a pretty reliable method for most drinking water samples. You're measuring at pH 7, and then you're measuring at pH 2. Next slide, please. Again, the precautions, chlorine dioxide is light sensitive, so when you're sampling, use the amber bottles. And it's also important to use dedicated, what we call aged glassware. What you really need to do is to pre-treat the glassware so that you remove any demand that's on the glass surface. And so using dedicated glassware really helps in these measurements. Remember, chlorine dioxide is volatile. You really need to fill the amber bottles to overflowing from the bottom, leaving no headspace. Next slide, please. Again, the four-step method, we're making measurements at pH 7 and pH 2. And so at pH 7, you can get both chlorine and/or chlorine dioxide reacting with the iodide, and which is then titrated. Then you drop the pH to pH 2, and you'll measure any chlorine dioxide that's in the sample, and you'll also measure chlorite ion in the sample. Next slide, please. So step A, you're measuring at pH 7 both chlorine dioxide and chlorine. Step B, you measure both chloride ion produced from step A and the remaining unreacted chloride ion. Next slide, please. Step C, you take another sample, you purge the chlorine dioxide, leaving chlorine and unreacted chlorite, make the measurement at pH 7, and then the fourth step, step D, you measure the unreacted chlorite ion produced in step C at pH 2. I've included the chemistry at those pHs. Next slide, please. Then you take your titrant values, volumes, and you plug them into the equations, and these will give you the concentrations of chlorine dioxide, chlorite ion, and chlorine. These methods are well spelled out in standard methods and other books and other reference materials. So if you do have any deeper questions about them, there's real good discussions of them, especially in the AWWA book. Next slide, please. One other thing about interferences with if you're doing the iodometric method, is that you have dichloramines and organic chloramines will titrate at pH 4. And some people, I get calls sometimes saying that their titration values seem to be a little bit high. So we're seeing, and they're saying perhaps it's the dichloramines, and or even monochloramine, which reacts at pH 7. It might give you a false positive for chlorine dioxide. Other possibilities, if you're having difficulty, can be manganese or some metal ions that will interfere with direct reaction or reaction with chloride ion at low pH. Next slide, please. One of the ways to get around this is to use this amperometric sensor technology. This is relatively new. It's offered by Palintest, and the data that's coming out seems to be pretty good and pretty reliable. It has some features that I like. The analysis time is very quick. If anyone has done some of these titrations, they can take time and they can be quite difficult to execute. But the analysis time is fast. It has a wide range, good precision, and a low detection capability. To detect chlorine dioxide at 0.03 or detect chlorine dioxide at 0.02, chloride ion at 0.02 is quite acceptable. Next slide, please. What's really nice about this option, and if you choose to go this way, one of the things is it has pre-calibrated sensors. It has a built-in degassing stage. It provides the sample bottles, and it also provides the procedures on how to do it. And you get a direct readout of your concentration in 2 to 3 minutes if you're doing the most complicated of tests. Next slide, please. The data that has been submitted regarding this methodology, as you see, this is actually the standard. Actually, you do these 7 methods, they could give you an MDL, but the numbers would be a little bit lower. But you see that the standard deviation is quite acceptable, coefficient of variance, also very nice. And so if you're using the standard method or you're using this new amperometric sensor method, we're seeing good results for chlorine dioxide. Next slide, please. And we're also seeing good results for chlorite ion at levels that one might expect to see. And again, the wide range makes it really quite ideal for making these measurements, something that a lot of times if you have to make lower level measurements, it becomes a little bit more difficult. But what we're finding is that this is actually a very nice alternative. Next slide, please. One of the other methods, if you're only measuring chlorite, method 300.1, the ion chromatographic method is really quite good. Some people have called it the gold standard when you're measuring residuals, chlorite, chlorate, and some of the other things. Again, as we mentioned earlier in the presentation, your monthly sample, your monthly analysis of 3 samples from a outside reporting agency or some approved laboratory is necessary, and it's typically a chlorite measurement. Next slide, please. NovaChem, we do have NELAC certification, we have state certifications, but typically what happens, you get someone to come on site and they take your, they check your laboratory to make sure it adheres to the standard. And then once you have certification, you're able to go from state to state, provided you work with the state and you pay your fee, and you go through the process to be regulated in that state. Next slide, please. If you look at EPA 300.1, it looks really nice. Now, this is a reagent water sample. It's not a drinking water sample. But the power of the method is clearly shown here. If you're measuring chlorite ion, which is peak 1, bromate ion, the important thing is to get separation. Chloride ion in a typical sample, this chloride ion would be very high generally. It would probably dwarf all these, but you still have resolution. Then this is an internal standard. It's called dichloroacetate, DCA, and then you have bromide ion and chlorate ion. This doesn't mean that you can measure this in 14 minutes. You can maybe get your result in 14 minutes, but the cycle time, generally out here, you'll have phosphates somewhere around 15, sulfates maybe somewhere around 20. And if you don't use ethylene diamine, because ethylene diamine actually forms a chloramine, which is not detected conductivity-wise. And what happens is you may need to use, once in a while I get a sample with thiosulfate or something. When I get that, I'll see a very long retained peak somewhere around 40, 50 minutes. So you can do that. I would suggest using ethylene diamine, but if you're in a pinch and you know you have lots of chlorine in your sample as a residual, you can use thiosulfate. Just let people know, and we can take care of it. Next slide, please. The accuracy of these of 300.1 is well documented. In my case, these are proficiency tests over time, maybe the last 8 or 9 tests that I have, and there's really good correlation from the reported value and the assigned value. Next slide, please. One of the things I'm really excited about, and it has to do with getting away from taking a sample and then waiting a day or 2 or 3 or more for a result. How can we do that? Well, there are options out there now. Even way back in 2006, we were reporting some online methodologies. And for here, you look at the chlorine dioxide residual, and as you can see, the blue line is the lab, and the red line is the online measurements. And actually, they're pretty consistent. If you look at averages, they're well within 0.1, and it actually appears like the online measurements seem to be a little better than what the lab measurements might be in terms of their spread of data. Next slide, please. The same is for chlorite. Again, these like way back in 2006, we were looking at these kinds of things, and as you can see, you have the blue, which is the online measurement. This kind of, I'm not even sure, purple kind of color, I guess. It's, again, this is the ion chromatograph. They did some field tests also. And as you see, when you're doing the assessment of measurements, when you're online, you want to see trends. You want to see what's going on. Are we building up? Are we losing things? Are we seeing spikes? But this shows the promise of the online measurement where everything looks right. By 3 different methods, we're seeing this rise in chlorite ion. And at the same time, if we're measuring chlorine dioxide, which is this aquamarine color, you can see, well, we should be seeing chlorine dioxide move down. If we're going to see a higher chlorite, basically maybe we'll see a lower chlorine dioxide, and this is what we're seeing. And so the idea of having the ability to measure this in real time or near real time and make adjustments is really quite nice. For instance, if you're trying to measure chlorine dioxide and all of a sudden you have a problem in your generator and you stop producing it, all of a sudden your system becomes out of quality, if you will, or out of control. The sooner you know it, the better you are. And so this online capability is really something that I think you're going to see more and more. And if you're forward thinking, I really do believe that you should look upon it as something that maybe can be implemented. Next slide, please. So if you look at laboratory measurements, they really are important to manage chlorine dioxide disinfection. The strategy that you come up with, the maintenance of the generators for operation and control of the generators, the need to meet the regulatory requirements, and of course, minimizing any unwanted disinfection byproducts really all of them come back to making some measurements, which then will allow you to make the proper changes or the proper control issue changes that you need to do to move forward and to have your disinfection system operate properly. I want to thank you so much for allowing me to present some things, and I'd like to introduce Stefan Andre, who will talk a little bit more about the online possibilities. Thank you.
Well, thank you, Bernie, for this in-depth discussion of sampling and monitoring of chlorine dioxide, and also your endorsement of online measurements of chlorine dioxide residuals. In my presentation of online analysis, we will discuss amperometric sensor methods, and I'll make mention of the DPD-based methods as well for chlorine dioxide measurement. But first, let's think about a suitable analogy that compares a graph sample analysis, as Bernie has talked about in depth, to an online analysis. I like to compare the graph sample analysis to a snapshot taken with a still camera, maybe even a 35 mil camera requiring the development of the film. As Bernie pointed out, sometimes it takes a day or 2 to get the analysis result back, versus the online analyzer that provides a continuous record of the measurement similar to that provided by a movie camera. So a much more informative and, let's say, proactive approach to measuring and controlling chlorine dioxide. Important to note is that the measurement principles of both these graph sample and online methods are not necessarily different. Next slide, please. Okay, so what is the principle of an amperometric measurement? I just want to go through this with you. Number one, it relies on an electrolytic cell, an anode and a cathode placed in a solution. In this case, our sample water, which is in the flow cell of the analyzer. The chlorine dioxide acts as an oxidizer, meaning it removes electrons from the working electrode or cathode, as shown in the picture here. The removed electrons then flow from the cathode to the anode. This electron flow or current is directly proportional to the disinfectant concentration, in this case, the chlorine dioxide concentration. Of course, we help out by taking that measured current that's measured via an ammeter and translating it to a chlorine dioxide concentration expressed in milligrams per liter. So that's the principle of the amperometric measurement. Next slide, please. Now let's take a look at one of two bare electrode amperometric sensor methods. I'd like to mention that the amperometric titrator is also a bare electrode type of measurement, meaning the actual electrodes are immersed in the sample to be measured. The first type of bare electrode online analyzer I want to speak to you about is a reagentless type. Main advantage here is it reacts very fast to a change in the chlorine dioxide concentration, usually less than 30 seconds. That, of course, makes it ideal for controlling, let's say, the chlorine dioxide concentration in a drinking water plant. But I'll talk more about that as we go through the presentation. Its platinum sensors are continuously cleaned by bombarding them with grit, especially sharp sand particles is what this grit is, and it ensures that ensures an accuracy and a consistency of measurement. There is one, let's say, important consideration, however. It does require a certain sample water consistency between calibration events. So we want consistent sample water quality for this type of measurement. Next slide, please. The second type of bare electrode sensor method differs from the first in that we now have the ability or flexibility of adding reagent chemicals. Reagent chemicals are not necessarily, let's say, in favor these days for discharge purposes, but they do have some advantages for certain applications. First, we can buffer the sample with a weak acid and add a level of consistency to that sample water. Secondly, we can add yet a second reagent, for example, ammonium sulfate, to react with any free chlorine present. The ammonium sulfate reacts with the chlorine, the free chlorine, to form a chloramine, which the sensor will not pick up. As Glenn explained, chlorine dioxide does not react with ammonia, so you don't get that byproduct. Lastly, the reagent style analyzer also allows you to calibrate with not just a grab sample analysis, but you can also introduce a prepared standard solution as a calibration solution. So there are two ways of calibrating this particular online chlorine dioxide analyzer. The reaction time for this bare electrode, again, is very fast, but the introduction of reagent chemicals does slow the analysis overall response time down quite a bit. So I show it here around 2 minutes. Next slide, please. The last amperometric type measurement I want to talk to you about is the membrane-based sensor method. It's quite popular these days. It requires the chlorine dioxide to first diffuse through a membrane, and behind the membrane is electrolyte, which acts as a buffer. So we do have this added measurement consistency that we mentioned is so important in a bare electrode type of measurement, not quite as important here. It is also reagentless, so there are no reagents to be added. It has a low capital cost. It does have longer response time, noted here, greater than, let's say, the bare electrode, because the chlorine dioxide first has to diffuse through the membrane. And it does require periodic maintenance, which can add to the life cycle costs, meaning we have to change the membrane and we have to renew the electrolyte on a periodic basis. Next slide, please. Lastly, just a quick mention of DPD-based methods. They are very popular for graph sample analysis, as you know, and also for some online measurements. But due to interferences, the DPD method has been removed as a standard method for determining chlorine dioxide. And as mentioned by Glenn, there are known interferences, oxidized manganese being one, chlorite analysis, chlorite ion being another. Next slide, please. I wanted to summarize the amperometric measurement types here in this little table for you. Again, comparing the three types I've discussed and allowing you to make a decision which analysis best suits your needs based on water chemistry, based on life cycle cost, or indeed capital costs. You can see the differences here in this slide. Next slide, please. Now let's take a quick look at automating the chlorine dioxide product feed for consistent chlorine dioxide residual in the process water. Actually, Glenn gave an example of flow paste, another word for flow proportional feed of chlorine dioxide. Here what we're doing is we're adding the disinfectant in direct proportion to the process flow. Process flow increases, the dose of chlorine dioxide feed increases proportionally. It's simple, but without concentration verification, and cannot detect a change in demand. And as Bernie points out, there are changes in demand throughout a day or throughout, let's say, the process of disinfecting the sample. Next slide, please. Feedback control, most importantly here, note the first bullet, only for closed loop applications with constant flow. Examples of those type of applications are cooling towers, various washing applications, and chilled water loops. Notice no mention of drinking water, so maybe not used for that. But why is the feedback control not suitable for drinking water applications where we do have varying flow? It's mainly because flow changes can happen very quickly, and they may therefore result in over or under feeds if we do not adjust for them very fast. Next slide, please. But lastly, here is for drinking water applications, here is the best control, let's say, methodology to be used, namely compound loop control, ties it all together. It quickly adjusts the feed rate due to changes in the process flow, so we measure the flow, and primarily adjust the feed rate due to that flow rate change. But secondly, we'd also take advantage of the continuous measurement that we've talked about in length and make changes to that disinfectant based on demand changes. So this is, let's say, the ideal control methodology for chlorine dioxide in drinking water plants. Next slide, please. In closing of just a few recommendations for successful online monitoring and process control for chlorine dioxide applications. Number one, perform weekly calibration checks. Note the word check does not necessarily mean the instrument needs to be recalibrated, but its calibration should be checked. Check the graph sample instrument calibration before adjusting an online instrument calibration. That's just from the school of hard knocks, understanding that sometimes graph sample instruments themselves need to be checked for calibration. Next, residual measurements below 1 milligram per liter. No, please. Back to the last slide, please. Yes, thank you. For residual measurements below 1 milligram per liter chlorine dioxide, do not recalibrate the online instrument if the gram sample result is within plus or minus 0.1 milligram per liter, or plus or minus 10% is the key here. So if your grab sample measurement is within 0.1, or in case of a 0.8 milligram per liter chlorine dioxide residual, if it's within plus or minus 0.08 milligrams per liter, don't adjust the calibration, is my advice. Lastly, for optimized feed rate control in feedback or compound loop modes, I suggest keeping those sample water lines short to reduce unnecessary control loop lag times. Often overlooked, and even though you may have very good online analysis, the control is hindered by not optimizing these sample lines, keeping them short. And now I'll hand the webinar back to Glenn for closing comments. Thank you.
Well, thank you very much, Bernie and Stefan. Those were very interesting overviews and presentations. Really appreciate both of your expertise on this subject matter. I'd like to take a moment to just summarize, and then we're going to have a session on some questions that have come up during the presentation. I haven't forgotten any of you, so we'll be back to that in a moment. Just to summarize, residuals, the chlorine dioxide, chloride ion residuals are measurable with the maximum contaminant levels, the MCLs, and the MRDL limits agreed by EPA and the state EPA groups. Chlorine dioxide at 0.8 ppm at entrance to distribution, chloride ion at 1 ppm max at entrance to distribution. There are a number of utilities that dose chlorine dioxide anywhere from 0.5 to 1.4 part per million. When you start approaching 1.4 part per million of chlorine dioxide as a dose level to, say, raw water, you can start bumping up on the chloride ion max MCL limit at 1 ppm. So there are some chloride ion reduction strategies that typically can be implemented, especially if you want to dose more than 1.4 part per million. And the most popular being to add granular activated carbon as a cap on top of the multimedia filter, usually replacing the same equivalent inches of anthracite with GAC. That could be, for example, 10 to 15 inches, or it could be a GAC bed, for example. The second popular method is to add a ferrous iron, such as liquid ferrous chloride or liquid ferrous sulfate, to the flash mixer just ahead of coagulation and flocculation. It takes about 3.1 milligrams of iron as Fe+2 per milligram of chloride ion. The reaction is very fast, occurs in seconds, anywhere from pH 5 to 8. The chloride ion goes to chloride, salt, and the ferrous iron gets oxidized by the chlorite to ferric, Fe3, polyferric hydroxide, which will precipitate during coagulation and flocculation. It can be removed, or it can be removed by a microfilter, for example. Next slide, please. So to quickly summarize, chlorine dioxide is being more and more proven to be effective and safe to generate using proper equipment. The equipment has been improved dramatically over the last 25 years. There are non-chlorine gas generation methods available that don't require chlorine gas cylinders to produce high purity, high yield chlorine dioxide efficiently. And last, I would say that chlorine dioxide is just one oxidant disinfectant in the toolkit. And most frequently, it's used in a multiple barrier type approach, typically dosed to raw incoming water ahead of coagulation and flocculation. There might be a second injection point to clarified water ahead of filters if additional CT credits are required. That's particularly true where chloramines are being used for distribution, and there are issues in terms of crypto and giardia CTs that need to be approved. So you'll find chlorine dioxide in many surface water plants. There are also increasing plants, groundwater plants that are using chlorine dioxide, especially where the groundwater has got high TOCs due to infiltration of surface water. Next slide, please. So we're going to turn to questions and answers. I've got a number of questions that have come up during the presentation that I'll speak to and address to the proper panelists. And some of these questions are, let me just pull them up. What type of contact time is needed for DVP reduction before aeration? I'll try to answer that, Bernie and Stefan. Really, it depends upon what the treatment objectives are with chlorine dioxide. If CT disinfection credits are one of the things that you're trying to accomplish with chlorine dioxide, obviously the more contact time, the better. If it's simply being used for manganese and iron reduction, THM precursor reductions, TOC oxidation, typically only about 5-10 minute contact time. You saw in Bernie's presentation, chlorine dioxide reacts very fast. And that is true in terms of its oxidation of the TOCs, oxidation of manganese and iron, which occur very rapidly. But if you're looking for CT disinfection credits, then you need more contact time. Also be aware that if you're applying chlorine dioxide before aeration, chlorine dioxide is a true dissolved gas. So you're going to be removing any excess chlorine dioxide that sees an aeration step, or say a carbonation step. So you want to apply chlorine dioxide well ahead of aeration, any aeration basis, preferably following. Now, there are some utilities that are co-dosing chlorine dioxide with chlorine ahead of aeration, and they have found that some of the low molecular weight THM precursors that get oxidized by chlorine dioxide get removed pretty efficiently during aeration. So just to sum up, the answer to that question is really, what are the treatment objectives? What are you trying to accomplish with chlorine dioxide? Second question I see is, what is the optimum pH of chlorine dioxide? I think I'll try to answer that also. Chlorine dioxide dissolved in water, high purity chlorine dioxide has a relatively neutral pH. In terms of its reaction capabilities, its disinfection capability is not really impacted too much by pH. So typically in most potable water plants, you're going to have water pHs of say 5.5 up to 9, and chlorine dioxide is effective across that range. You'll also find that if you're trying to oxidize manganese, that manganese will be removed and oxidized more efficiently at an alkaline pH, typically pH 7 to 8. There's a lower dosage rate below 7. It works below 7, but it's not as fast as in the alkaline pH range for manganese. Another question was, how quickly should a sample be run to check for chlorine dioxide and chlorite? Bernie, I'm going to let you answer that question.
Thanks, Glenn. I think that's pretty much stated by EPA and the state regulators. There's a real process here. You take your sample, you fill it properly in the proper container, no headspace, and then you chill it. I believe the time frame is within an hour and a half, you should be okay. But if the water's got high demand, understand that what happens is you may lose a little bit of chlorine dioxide. And so what you need to do is to take care in how you sample it and how you store it before you get to the lab. But I think all reasonable places are saying you could probably, if you get it back to the lab within an hour, you should be, that's a reasonable goal.
Okay, Bernie, another question is, why are you recommending EDA, I guess that's ethylene diamine, for dechlorination in place of sodium thiosulfate in the chlorite step?
Well, there are a couple reasons. The first one is that's how it's specified in the in the method, EPA method 300.1. So if you're going to run 300.1, that's fine. Secondly, ethylene diamine is an effective mask for chlorine, and so it'll complex chlorine and remove chlorine from your sample quite quickly. And most importantly, it doesn't react with the conductivity detector. So you don't see any effect of it. So I have put it in at relatively high concentration, seeing no change in output. Now, compare that to thiosulfate. What happens with thiosulfate is you have a charged species when it complexes. And so it's highly retained on the column, and it increases the cycle time of the analysis. So if you're running, say, a test with ethylene diamine, it may take 20 minutes for a cycle time, maybe 25 minutes, depending on your flow rate and sample size. If you use sodium thiosulfate, you will extend your cycle time to maybe 45 minutes or longer, depending on how much thiosulfate is in the sample, because it is now a charged species, which then reacts with the conductivity detector.
Another question, Bernie, what concentration of chlorine dioxide is the calibration sample for the amperometric method?
Well, I think you need to know a few things. And again, the amperometric method, by doing the titration and not using sensors, is really how good is your operator? How good is the person doing the testing? So you need to, you really need to know the capabilities of your operator. If you're going to run, if you're not dosing high, obviously you want a lower standard of some type. So how good can you make measurements around the 0.1, 0.2 level versus the high level that you could put in is 0.8. So it would be somewhere between, I would say, 0.2 and 0.8 with the titration equipment. Again, those lower measurements, very operator dependent on accuracy. So I think it really depends on your operator. It really depends on what your dose is, and again, what you're using the number for. I mean, if you're generally running higher, I would probably use a midline value, generally speaking, somewhere between 0.2 and 0.6, just to make sure that your operator is doing fine, because if you're down low, it's much harder to make those measurements.
Okay, thank you, Bernie. Another question, do some municipalities using chlorine dioxide and that have perchlorate, do they blame the chlorine dioxide addition? Do they understand the connection to bleach decomposition? Bernie, you want to try to answer that one? I may add.
Well, I think people are becoming more and more aware of it. Again, right now, chlorate and perchlorate typically aren't something regulated for chlorine dioxide use, but I do know that there are certain states that send me samples that they want perchlorate measurements. So the industries are aware, certainly the chlorine industry is aware of the perchlorate formation issue. Does that answer that question, Glenn?
I think so. I think, there have been some really good studies by AWARF and presentations by AWWA over the past few years. I think we all understand that bleach degradation can be a problem in terms of chlorate formation and oxidation formation.
Right. There's a calculation out there that NSF uses that you can make a measurement and you can see if it reaches an acceptable level. It's called the normalized result. And when you're looking at bleach, there are a lot of people will send me a sample of bleach and say, does this meet the criterion? I got to report it every quarter or whatever. And I measure the chlorate value, and then I can plug it into this equation that'll give me something called the normalized result. You have to provide what's called an MUL. I forget what it's an acronym for, but you can plug it into the equation and you can make that calculation. Typically, a chlorate value in the bleach, say 12% trade, you can probably have more than 2,000 milligrams per liter of chlorate ion and still make it. I would say if you're around, typically when you're delivered, if in the first couple days, you might be at 200 parts per million. So if you're at 200 to 2,000, you're probably okay. Well, you are okay. If you get above 2,000, 1,500 to 2,000, you better start taking notice.
Okay, thank you, Bernie. I'll just add, this is Glenn. There's a lot of folks that are moving toward on-site generated bleach generation at 0.8% strength, 0.8%
right.
bleach. And the decomposition of 0.8% bleach is very minimal, less of an issue. There are chlorine dioxide systems available in the marketplace today that can use weak bleach, 0.8%, as one of the starting raw materials to help generate chlorine dioxide. Also, right. Typical dosing of chlorine dioxide is about maybe 1.4 ppm, in that range, sometimes as low as 0.5. So in a flow-based situation where you're dosing, say, a 1,500 to 2,000 part per million chlorine dioxide concentrate, chlorine dioxide dissolved in water, to an injection point, the actual dose rate going into the water is, say, 1 ppm. So you have a dilution factor typically of 1,500 to 2,000 in that range. We have not seen, in most cases, a chlorate issue from chlorine dioxide systems that even use bleach as a starting raw material, be that 12.5 or 0.8% or 5 to 7% in that range. Doesn't mean that's true in every case, but oftentimes what I've seen is non-detect chlorate. I'll also add that the WHO, the World Health Organization, guidance limit in potable water for chlorate today is 0.7 ppm. And when chlorate is measured, typically from a chlorine dioxide program contribution, it's typically less than 0.3 part per million to non-detect. Another question that's come up is, what is more advisable to use in water distribution line, chlorine dioxide liquid or chlorine granules? It's Glenn again. I'll try to answer that question. It really depends upon what you need to accomplish in terms of residual out of distribution. It's more common to use chlorine or chloramines or chlorine granules for the distribution system, but there are a few utilities here in the U.S. that use chlorine dioxide for both primary and secondary disinfection. Those usually are very short distribution systems. Chloramines and chlorine are going to last longer from a residual standpoint than chlorine dioxide. If you look at what happens in Europe, it's very common to use chlorine dioxide for a distribution system. But the reason for that is the distribution systems in common to use chlorine dioxide for the distribution system residual. Not unreasonable to look at, but not very common. I think we're coming up toward the end of this session. I don't see any other questions unless someone wants to ask another question. I really appreciate the attendance today, Bernie's expertise and Stefan's expertise in their presentations. There is at the end of this presentation, if some of you want CEU's credits for attending the webinar, there is a web link, which is www.awwa.org/credits, that you can go to register for credits having attended this webinar. And I understand that the printed certificates will be available within 30 days of the webinar. The presentation has been recorded, and you will have access to the recorded presentation. We really appreciate your attendance today. I see no further questions. Thank you so much, and everyone have a nice day.